Higgins, and she's from CU Boulder. So today, Josh will be talking to us about using GPS signal-to-noise ratio observations to detect and characterize the volcanic plume associated with the 2003 Soufrière Hills Volcano dome collapse.
Yes. Thank you, Aisha. So my name is Josh Russell. Thank you all for coming. As Aisha said, this summer I worked with Braun at UCAR and Glen Mattioli here at UNAVCO. Today I'm going to talk to you guys about the 2003 Soufrière Hills Volcano dome collapse and the resulting plume from that, and how we use GPS SNR to actually examine that plume. So this is, sorry, it's kind of falling off. So this is an example, this is a before and after picture of the dome collapse that occurred on the 12th and 13th of July, 2003. Approximately 210 million meters cubed of material was removed at the time, much of which was thrown into the atmosphere, and that's what we're interested in detecting. So the main objective of this project is, again, to use GPS signal and noise ratio to actually detect the temporal and spatial extent of this plume that occurred. So some of the motivation, first, the Soufrière Hills volcano plume has not been very well studied in the past. And additionally, the volcano itself is a good place to study because we have good past data of when the eruptions actually occurred that we can compare to our observations. And secondly, the capabilities of GPS SNR for examining volcanic plumes has not been fully explored. So this is the regional setting. Montserrat's located in the Caribbean, as you can see. If we zoom in, we can see the three GPS stations that we're using in this study. We actually had a fourth one, but it didn't have enough data for us to use, so we kind of had to throw it out. But we still do have a pretty good distribution of stations around the island. So GPS SNR is not typically used for plume studies. It's kind of a new thing. So last year, Christine Larson at the University of Colorado Boulder published a paper showing that GPS SNR can be used to detect volcanic plumes. And so this schematic is just kind of a little illustration of what's going on. So a GPS signal that passes through a plume becomes attenuated, and we can measure that attenuation as a decrease in the signal-to-noise ratio. So in my talk, I'll touch on three main points. So the first thing we'll look at is the temporal plume detection, just to make sure that the timing matches up with the previous studies. Second, we'll look at the spatial extent of the plume, and that has not actually been fully explored yet, so that'll be kind of a first look. And then third, we'll look at the geometric analysis of plume height that we can do having a certain satellite station geometry. So I'll dig a little deeper into the method that we use. So I'd like to orient everyone to this graph here, this plot, because it's kind of central to this talk, and it'll pop up quite a bit more. So this is, the way you can think about this is a receiver right in the middle of the plot, and directly overhead is 0 zenith. And so the radial axis is measuring zenith. And as you go to the edge of the circle, you're moving towards the horizon. And so each of these tracks is a satellite moving overhead. And this is just a normal day, I think 10 days before the plume occurred. This is the normal gain pattern that you see from the signal-to-noise ratio. So the first thing we want to do is calculate an average in order to eventually calculate a residual. So the way that we did this was we took 2-degree averages of azimuth and elevation along each of these satellite tracks. And for this example, we did it over 10 days where there was no plume activity. And you can see that it looks very similar to the observed data, which is what we would expect. And so to calculate a residual, we just subtract the average from the observed, and we end up with, in this example, approximately 0 residual, which is what we would expect if there's no plume around. So attenuation will show up in these residuals as negative values. So first we'll look at an example of the plume being detected in the temporal domain, I guess. So here we have a time series of the residual, SNR residual. And so in the black line here, we have our detection threshold that we use. This is 2 days before the eruption. And so the detection threshold that we chose was 4 standard deviations below the mean. So anything below that is kind of an anomaly, and it's considered a plume detection. So now if we look at during the eruption, we see very large attenuation. This red line here marks the eruption start time of the main collapse as determined from seismic data. And you can see a very close correlation between the collapse and the dome collapse and the attenuation that we're seeing, which would be the plume. And so now we'll look at the same station, same day before the collapse. We see in the spatial domain, there's approximately 0 attenuation, so it's almost completely white. And if we look during the collapse, we see a significant amount of attenuation, the negative values being signal attenuation, the positive values being signal amplification. So now we'll look at the 3, that was just for a single station on the day of the collapse. Now we'll look at all 3 stations on the day of the collapse. And you can see a very different plume signature at each of the stations, and that tells us a pretty interesting story about how the plume was moving on that day relative to each of the stations. So in a previous study, it was shown or observed that most of the pyroclastic flows were actually moving down this Tar River Valley in yellow. And so from our data, we draw from this that the plume first moved from this Tar River Valley north over Herm. So that's why we're getting this sort of north-south trend and the attenuation. So it began moving north, and then as it was moving towards MV01, it eventually dispersed as it was traveling. And by the time it actually got there, it was kind of covering the sky over MV01, and that's why we're getting this attenuation from a bunch of different azimuths, not this sort of focused attenuation that we're seeing at Herm. And this makes sense for what we're seeing at Souf, because if the plume is actually going northward, Souf is south of the vent, so it's not going to show as much attenuation as the other stations did. And additionally, Souf has this, just due to the geometry of the satellite tracks, we have this blank spot here, this kind of blind spot to the north that Souf can't resolve, and that's essentially where the plume would be detected from. And I should mention there is actually one satellite track right here that will come into play a little bit later on our analysis of the plume height. And so we were able to find a satellite image of the plume, and it was in fact moving to the northeast from this GOES satellite image. And that sort of trend we can see here on Herm, which was the closest station to the plume. So now we'll focus on this Souf station that I mentioned earlier. It seemed kind of insignificant at first, but it turns out we can actually use this single satellite track to estimate a plume height. So here's just a schematic showing the geometry of the plume receiver plume geometry. And so the idea is that as the satellite is rising in elevation, which is going from the edge of the circle towards the center of the circle, it's pretty much directly in line with the Soufrière Hills Volcano, as you can see from the diagram. So there's actually 2 scenarios. We're not sure if the plume was directly over the volcano or directly over MV01, since they're kind of in a line right there. So we calculate heights for both of those using the elevation angle of the satellite whenever attenuation stops occurring. So this transition from attenuation to no attenuation tells us the maximum height of the plume. We calculate a plume height above the volcano as 3 to 3.5 kilometers, and a plume height above the MV01 station for 9 to 11 kilometers. And this is lower than previous estimates of maximum plume height that showed 15 or approximately 15 kilometers in height. So there are a couple of reasons why our estimate might be a little bit lower. I think one of the obvious ones might be that the plume is moving to the north from the Tar River Valley, and we're actually, from Souf, we're only seeing sort of the edge of the plume. So we're possibly not seeing the maximum height of the plume. We're just seeing a height of the edge of the plume at that time. So our conclusions. First, we were able to provide a first-order constraint on the dynamics of the plume. We saw that it was moving to the north, roughly, and satellite images confirmed that. And so that's actually hasn't been done before using GPS SNR data. And so second, we were able to estimate a plume height. It was a little bit different than previous studies, but it's possibly due to the fact that either we're not imaging the maximum height of the plume because we're sort of off to the side, or even the plume hasn't risen up to its maximum height yet by the, when we're actually sampling the plume. So we're kind of getting it on its way up. And so this work acts as a preliminary basis for future studies using SNR data to actually constrain plume geometry. And I would like to thank everyone who has helped me through the summer. My mentor has been great, and it's a very positive experience for me. Stephanie Higgins, my writing mentor, I don't see her around, but she was really great and helped me out a lot throughout the summer. So thank you, everyone.
All right, thanks, Josh. Do we have any questions? Jackie?
I know your focus was on the attenuation of the signal, which were the negative values. I noticed some positive values, which was the amplification. And do you have any possible hypotheses as to why the signal could have been amplified?
Actually, we're still not quite sure why that occurred. Actually, so this is the day of the collapse, and we actually have data. I think I have it here, but I decided to take it out because it's kind of messy. But we had data for several days before and after the plume. So actually, this is the day before the collapse, the main collapse. This is the day after, or the day of, and then the day after. We see the same signal coming up before and after the collapse. So we're not exactly sure how there would be amplification on multiple days in a pretty localized area. I think one way to explain it might be just ash because it is the closest station to the actual event, that it may just be ash around the receiver, and multipathing, sort of increasing the signal just from multipaths, like constructive interference. So I don't know, that's something we'll have to look more into, I guess, maybe from future studies if other people see the same thing, because I don't think anyone has ever seen that before. So kind of interesting.
Are you able to use the amount of attenuation you see to say something about the density of the plume?
Yeah, so that's something that we were hoping to get to this summer, but actually didn't have time for. So we're going to try to do some forward modeling to see if we could kind of constrain, I guess, plume radius and plume density, and see kind of if we can figure out like an attenuation as a function of path length, taking into account density. So we actually didn't have time to do that, but that's definitely something that I would be interested in learning more about. So.
Did you make any plots of time versus the signal-to-noise deviation, so you can see like the onset of the attenuation and so forth?
Yeah, so that was another one I didn't include because it was kind of, I don't know if it's, yeah. So that's for each station. And actually, this is only for the day before and the day of. There's more activity on the day after. But so MVO or HERM pretty much sees attenuation starting from the day before until it runs out of data. So it's probably being destroyed by pyroclastic flows and sort of shuts off. So we don't have data after that. But actually, and it was Mattioli 07, I believe, they actually observed pyroclastic flows the day before the eruption, and we can actually we can actually see that here from Herm. And it's the only one that can see it, but it is the closest to the Tar River Valley. So, yeah. And these other black lines are also from seismic data, but, yeah, earthquakes. So, associated with the subsequent eruptions. But the red one is the one that we were looking at in this study, or in this presentation, which was like the main one, the biggest dome collapse. So, yeah. So, yeah, there's actually a third one as well on the next day that's associated with this one here. And so, yeah, not quite sure.
Just could the positive values in signal-to-noise ratio the day before, for instance, on Herm, like a sensor that's closest to the volcano, could that be used as a possible early warning system? Like, or something to kind of, what do you think about that?
I think so. In Larson, in her paper that she published, she kind of alluded to this being just the method of detecting plumes using SNR as being a possibility to be used in like real-time monitoring of plumes, just because we don't have to take into account atmospheric fluctuations or anything, because SNR is actually not sensitive to water vapor. So, yeah, I think that's a possibility in the future, sort of having an algorithm to just do it on the fly, yeah.
Going off of Kaylee's question about characterizing the nature of the plume, do you personally and scientifically feel that this technique has implications for like other types of plumes, like not necessarily plumes, but maybe smokestacks or other types of atmospheric events?
Yeah, I don't know. That's interesting. I never really thought about that. Yeah, I suppose so. The only problem would be that you would need a lot of GPS receivers around. So that would be like one limitation.
So you can market to like, you know, certain companies that have smokestacks, and
yeah,
do you want to
buy our GPS receivers and put them out? Yeah, I don't know, but yeah. Uh-oh.
Okay, so that leads me to my question, which is, so you've detected this anomaly or perturbation in signal-to-noise ratio. I know you're a physicist. Could you give me some indication of what the physical mechanism is associated with changing the SNR?
I don't know. I guess scattering from particles in the plume causing a decreased signal that actually reaches the other side of the plume. So there would be an attenuation as a function of path through the plume. So as it travels farther and farther, more signals are becoming scattered and less of it reaches the other side. Yeah, coherently.
That sounds like a good explanation. So then that scattering would be dependent on what parameters of the particles in the plume?
I would assume grain size would be the biggest one, just because large grains would sort of impede the signal. If you had a rock, you know, if you blew it up to the size of a giant boulder, you couldn't pass any signal through that. So, I don't know. That's what I would say. Yeah. Oh, maybe.
So how about smokestacks then?
Oh, yeah. Yeah, I guess that would be water vapor, right? Yeah. Forget everything I said. No.
Glenn, this feels like a comp for a PhD. Yeah. All right, any other questions? All right, thank you, Josh.